In the last two lessons of this module, we'll discuss how to compare drainage water quality practices based on cost. When you start to think about the costs of the different conservation drainage practices, one of the first things to think about is that costs occur at different times for different practices. For example, the total cost of doing a winter cover crop all occurs within one cropping year. In other words, the cost of planting and terminating that cover crop are annual costs that would be incurred every year you wanted to do that practice. This is very different from a structural practice like a bioreactor, for example, where the vast majority of the cost of the practice occurs in year one, but you receive the water quality benefits for the 5 to 10 year life of that bioreactor. When costs occur at different times for projects or practices, in our case, the procedure of discounting is used. This is sometimes called a discounted cash flow analysis. Discounting is an analysis method to value costs or investments using the concept of the time value of money. Question: if I offered you $5 today or $5 in 100 years, what would you take? I suspect most of you would say the $5 today, and that is an example of the time value of money. $5 today is worth more to you right now in present value than $5 in 100 years means to you right now in present value. For our application, because conservation practices each have different costs that occur at different times, we have to use the process of discounting to compare practices. In this process, we discount each of the costs involved with a given practice depending on when those costs occur, and then bring all of those costs back to a chosen point in time, for example, summing all of the costs once they are calculated as present value costs. That allows us to compare, for example, the total present value cost developed for each practice. But that total present value cost is not the end of the story, because then we can use the process of amortizing to spread those total practice costs back out, so we end up with $1 per year of functional life of the practice. But before I go any further, I want to issue the caveat that this is not an economics course. If you are interested in fully capturing the costs and every nuance of discounting and compounding, you should take an economics course. To do this whole process, you have to know for your practices of interest, what are the itemized costs, when do those costs occur, and if those costs are recurring or one-time costs. Let's do an example for saturated buffers. Starting with the itemized cost, for example, you'll need parts and pieces, a control structure, drainage pipe, parts and fittings. There could also be material freight or shipping costs. Depending on how long your planning horizon is for your cost analysis, you'll need to replace the stop logs in the control structure maybe every 8 to 10 years. You'll also have labor costs for the installation, so you'll have to estimate or know from an invoice the number of hours required for construction as well as the contractor's hourly rate. Don't forget, there could be a mobilization cost charged by the contractor to get them even out there on the site. You could also consider including a small time compensation for the farmer to check the saturated buffer a couple times a year to make sure it's working properly. One last note that I'm purposely leaving out here for simplicity, but is becoming increasingly important for structural practices, is the engineering design costs. These costs will not be immaterial when we consider the scale of wetlands, bioreactors, and saturated buffers that our state strategies have called for across the Midwest. I'm just not including them here for the sake of simplicity. And then back to our example, moving to the next columns in our table, most of these costs for this structural practice of saturated buffers occur in year one as a one-time cost, but you do see there are also a couple of recurring costs that occur throughout the practice life. This is why, to calculate the total cost of a given practice, the process of discounting is required. Let's do another quick example for cover crops. I organized this itemization a little differently because this is a management rather than a structural practice. But you see, for the planting, you consider seed cost and equipment and labor cost, and the same type of considerations for termination, but obviously your itemized costs would depend exactly on how you decide to terminate the cover crop. So what I'm showing here is just a general example. The thing I really want to illustrate is that all these are recurring costs that occur every year that you do a cover crop. For this in-field practice, you could also quantify the cost of a crop yield impact due to the cover crop. Some research shows a small yield penalty, and that of course could be economically valued here as a recurring cost, or You could take an approach that doing cover crops for a long time improves soil health and may eventually improve crop yields. That wouldn't be a cost, but rather an income stream. That's out of my wheelhouse, and I'm just illustrating this as an example, but you can see that wouldn't be an effect that doesn't start right away, but it would be a recurring impact, and you can value that using our discounting procedure. In this process of comparing practices based on their costs, once we have all the costs itemized and know when those costs occur, we can actually start to do the math of discounting those costs back to a present value. You can also discount to a point in the future by calculating future value, but our convention here in this lesson is to discount back to present value. The decision tree I'm showing here gives the equation to use to discount based on what type of itemized cost you have. Is your particular itemized cost a single one-time sum, or is it a recurring cost, in other words, a series? Let's go back to that example about the $5 today or the $5 in 100 years. In this flowchart, both of those scenarios are single sums. They are not recurring costs, so it's relatively easy to know what discounting equation to use. In these equations, V naught or V sub O is the present value, which is what we want to calculate. V sub N is the future value. I is a discount rate, which we haven't talked about yet, but in this example, we'll use 4%. And N is the number of years. You can feel free to pause the video and work these equations out for both scenarios. Or you can just watch me do it. Starting with the $5 today. This one is easy. You don't have to actually calculate anything because you know it's already in present value. That $5 occurs today. However, you can also do the math if you really want to by plugging in 0 for N, meaning 0 years or present value. Anything raised to the 0 is 1, and you see mathematically $5 today is worth $5 in present value. Moving to the other scenario, me giving you $5 100 years from now, you plug in 100 for N in this single sum equation, and again the discount rate, or I, is 4%. We use that as a decimal rather than as a percentage in these equations. And then working through the math, you end up with that $5 100 years from now is worth about 10 cents in present value. So hopefully you made a good decision. Although I'm not actually giving you $5. Sorry. Those are just examples using single sums, but for this discounting process, you apply the correct equation for every single one of your itemized costs, which is why you also need to know when each itemized cost occurs, because that helps you figure out what equation to use. Once you have brought all of the costs that occurred over the life of the practice back to today's dollars and then summed them into a total present value cost for the practice, then we use what's called a capital recovery factor to amortize that total cost into an equal annualized cost. That tells us how much does a given practice cost each year over the life of that practice. I've mentioned the term discount rate a couple times, so let's define that. In finance, this is defined as the interest rate for lending set by the Federal Reserve. There are two kinds of discount rates. A real discount rate does not include inflation, whereas a nominal discount rate does consider inflation. I will highlight again that if you're really interested in this stuff, you should take an economics course. The important thing for us to know is that the discount rate is what makes it algebraically possible to compare cash flows occurring at different times. And fortunately for us, there is a federally published discount rate that applies to water-related projects. Most of these water-related projects are Army Corps of Engineers projects, for example, but it's still a handy rate for us to use for our purposes. I pulled the most recent 2022 water-related discount rate from the Federal Register, and you see that at 2.25%, it's quite a bit lower than it was even a couple years ago. The other federal rate for non-water-related projects has also decreased over time. And I happened to find this graph showing even a negative discount rate from 2021 from the Office of Management and Budget in DC. Just keep in mind that the appropriate discount rate changes yearly, and these rates play an important role in being able to appropriately account for that time value of money. One of the handiest resources for this type of work are custom rate surveys. There may be custom rate surveys like this performed and published in other states, but I love to use the Iowa State one, which is updated every year. This resource gives averages and ranges of costs for common field operations that are performed as custom services. You might be wondering, How could you estimate the cost of drilling a cover crop, for example, to plug into our discounting equations in terms of dollars per acre? If that were performed as a custom service, you see that right here, that average charge is $17.35 per acre. Or how would you estimate the cost of using a backhoe to excavate for a bioreactor? Again, that information is right here in the custom rate survey, along with a nice range if you want to be conservative or less conservative. This custom rate survey provides great rule of thumb values to use for cost itemization. To wrap up this lesson, I'm showing graphs of how several practices compare when their costs are all developed in a consistent way using a discounting procedure. The graph on the left shows the equal annualized cost in dollars per acre treated per year, and the graph on the right shows the equal annualized cost in dollars per pounds of N treated per year. 2 points here. Firstly, while each practice has a single cost efficiency identified with the diamond shape, each diamond also has error bars to show the variability. Just like we discussed in the first video for this module, these error bars are important so we don't have a false sense of precision. My second point is that for drainage water, the constructed edge of field practices tend to be relatively cost efficient because they are specifically designed to address drainage water. On the balance though, a practice like a bioreactor doesn't provide any other additional benefits, which is why I like to consider not just cost and practice performance, but ecosystem services, barriers, trackability, stackability, all of the things we talked about when I compare practices. The last lesson for this module coming up next is an example of this discounting process done in Excel. So I'll see you next time in Excel. Thanks for joining.